Okay, so this is going to be the video about the history of atomic theory here. Um, there's a lot of words in this, so I'm not going to say all the words. I'm going to give you the short version in my speaking. You should really pause the video, read, take a look at this stuff, and yeah, so let's get going. All right, long time ago, this guy, Democritus, basically he came up with the idea that there was some uncuttable piece of matter that everything was basically made of, and he called it atomos, and that objects were made of fundamental particles that were related to their macrophysical properties, right? Like bread would be made from tiny bread particles and dogs from, tiny dog particles. So that's the very beginning of our understanding. Then we skip ahead many years to conservation of mass in definite proportions. So conservation of mass we've talked about, or maybe we haven't talked about, but the mass of the products is always equal to the mass of the reactants, and this was thought up by this gentleman here, Antoine Lavoisier, who, and this is his wife, who was his kind of, I guess, lab assistant who helped him in all his science and is credited with helping to make a lot of his discoveries. And then we've got the law of definite proportions, right? Chemical compounds always contain the same proportion of elements by mass, and that was Joseph Proust, and this is in the late 1700s. Then we've got this guy, Dalton, who comes up with one of the first atomic models, as well as the law of multiple proportions. All right, you can read the law of multiple proportions there. And this is Dalton's model. All right, his model was basically the billiard ball model, and that atoms were tiny particles, and that they were indestructible, and that all atoms of the same element were identical. So then, a while after Dalton, about 100 years, this gentleman, J.J. Thomson, comes along and discovers the electron. Right, and he did this by shooting particles through what's called a cathode ray tube. You can check those out. They're pretty cool. TVs used to be made out of them. And he was able to calculate the mass of this particle and found that it was much smaller than the hydrogen atom, meaning that Dalton's model was not correct anymore. So Thomson came up with his own model, which was called the plum pudding model, where the electrons were embedded inside the positive atom like plums in plum pudding. He used this model because he was English, and I guess at the time, English people liked plum pudding. So there you go. Then this gentleman comes along, Rutherford. This is not the last time we will hear about Ernest Rutherford. He did some other stuff. And he discovered the nucleus. Right here, you can read all this stuff, pause the video, read it. This was his experiment that he used to discover the nucleus. Basically, he had this radioactive thing. He didn't know what it was shooting out, but he knew that it was very small particles. They shot here. Some of them went through the foil, some of them deflected, some of them even came bouncing back. Right, so he knew that something in this foil, one, was massive enough to deflect or send bouncing back the radioactive particles that he was shooting at it, but concentrated in a specific area enough that it allowed many of these particles to go through. And so what this told him was that there was something small and concentrated in the atoms that was very massive, and there was a lot of empty space around this. And so he said it was the nucleus. Then comes Millikan, right? And he gives us a little more information about electrons, right? And this is a picture of him and the apparatus he used to do this, which involved oil droplets. You can read about it here, but he calculated the exact charge of an electron to be a fundamental value, which way back in 1909, he was able to calculate this value within 1% of the currently accepted value, which I think is pretty great considering the technology that he used in 1909. After Millikan, right around the same time that he's talking about all these electrons and stuff and figuring out the charge, and that we start to understand that there's a nucleus in the atom, we start to have people talking about quantum theory. And this is the current theory and model of the atom. And it all begins with this gentleman here, Max Planck. And so he conducted this experiment where he was measuring what he called black body radiation. And basically what he discovered was that the energy coming out of these pieces of metal that he was heating up and the energy from the electrons was quantized, which means it occurs only at whole numbered integers, like someone going up a flight of stairs, right? Electrons cannot exist between these levels and make jumps when they receive enough energy to move to the next level, or a jump when they move back down, right? He called this smallest amount of energy a quantum, which means fixed amount, because they can exist at fixed amounts of energy. So then this gentleman, Niels Bohr, takes this idea and runs with it and presents his idea of the atom, which was negatively charged ions orbiting, or negatively charged electrons, orbiting around the positive nucleus at fixed or quantized distances, like planets around the sun, which is why his model is often called the planetary model. And his theory was heavily based on the work of Planck and others who had shown that radiating energy was quantized. So this is the Bohr model, which we now know is wrong. It was didn't last long, but it did win him a Nobel Prize. So, good job, Niels. This is what the quantum model looks like, which is not like electrons orbiting around a sun. This looks very different. And this model is thanks to many discoveries that were made from the 1920s to 1940s. We can talk more about this in class, but many discoveries were made during this time because there was something rather important going on in the world at this point, and a lot of money was being thrown around to understand atoms and nuclear power. So ask me about that. We can talk about it in class. Read this slide. Talks about the quantum model. But here are some people who had a lot to do with the development of the quantum model. One of them you should recognize. And then this guy, some dude named Albert Einstein. So Albert Einstein and Louis de Broglie, they are two halves of what we call wave-particle duality. So Einstein won his Nobel Prize for the study of the photoelectric effect. And basically, you can look this up and read about it, but what it shows is that energy is carried in discrete packets, or photons, that have characteristics like a physical particle, right? So light and energy is carried in photons that have characteristics and abilities like a physical particle. De Broglie, on the other hand, his research showed that electrons have a measurable wavelength, a property normally only found up in light up until this point. So he proved it by measuring a diffraction pattern made by electrons fired at a crystal of nickel. So these two showed that electrons can act like light, and light can act like electrons, and that they can interact. This guy, Schrödinger, Erwin Schrödinger. He is responsible for the Schrödinger equation, which is super important in quantum mechanics and the quantum mechanic model. Now, the equation is super complex, requires a lot of pretty involved mathematics and calculus, and it's all to find the probability of an electron at a particular distance from the nucleus. And the orbital shapes that we'll study, S, P, D, and F, are generated using his equation. Should also remind me to talk to you about his cat, which is a pretty interesting story. So then this guy, Werner Heisenberg, he is responsible for the uncertainty principle, which bears his name, the Heisenberg uncertainty principle. And basically his principle deals with the amount of uncertainty introduced when measuring the properties of extremely small or extremely fast moving objects. Electrons fall into both these categories. And so ultimately what he's talking about, the standard deviation or uncertainty associated with a measurement, means that you cannot know both the position and the momentum of an electron with any certainty at the same time, right? You can know either where they are or how fast they're going, but not both at the same time. And so that concludes our adventure through the history of atomic theory. Like I said, you should have been pausing the video and reading. You can also do some more reading about these and the experiments that went along with them and all these gentlemen. And yeah, there we go. See you in class.